All right, let's jump right into one of the biggest questions out there. How do we actually learn? I'm not talking about just memorizing facts for a test, but how we find the real, meaningful patterns in a world that's, well, pretty messy. We're going to go beyond the data to look at the logic of learning itself.
Okay, to kick things off, here's a simple little puzzle for you. Which number comes next? 2, 4, 6, 8. I'm willing to bet you immediately thought 10. And yeah, that's a great answer. Based on the super simple rule, just add 2. But what if the rule was something weirder, like the sequence of even numbers that you can't divide by 5? Well, then the next number is actually 12. Or what if the real rule was some ridiculously complex polynomial that just happened to spit out those first 4 numbers? See, the point is, there are literally infinite possible rules that perfectly fit the data we've seen so far.
And that right there is what we can call the pattern problem. Whenever we're looking at a set of data, whether it's a number sequence or results from a science experiment, we have to pick which underlying pattern is the right one. So how do our minds so easily, so instinctively choose the add 2 rule over all those other way more complicated options? And look, this is way more than just a brain teaser. This is the absolute core challenge of how we reason about anything. From a little kid figuring out how language works to a massive AI model learning to spot cats in photos, the job is always the same. You have to separate the real, meaningful signal from all the random, useless noise.
So how do we solve this? How do our brains do it almost without thinking? Well, the answer comes from a surprisingly beautiful idea from information theory. It's a powerful guide for picking the best explanation, and we can call it the compression principle. At the heart of this whole thing is what's known as the minimum description length principle, or MDL for short, and it's a really simple but profound idea. It just says that the best theory, or the best model, for any data you have is the one that gives you the shortest, most compact description of that data. The goal is to be as brief as possible.
And this leads to a really cool kind of mind-bending insight that changes how you think about learning. Forget all the complicated math for a second and just picture zipping a file on your computer. According to this principle, real, genuine learning is basically just a very sophisticated form of data compression.
This analogy makes it all crystal clear. A good theory, like our add 2 rule, is like a brilliant compression algorithm. It finds the real pattern, throws out the noise, and bam, you get a tiny, efficient little file. A bad theory, on the other hand, it misses the pattern completely. It just memorizes everything, noise and all. And the result? A huge bloated file that's no smaller than what you started with. Okay, so let's get into the nitty-gritty here. When we talk about the shortest overall description, what are we actually counting? Well, it turns out this description is made of 2 different parts that are kind of in a constant tug of war with each other.
Here they are. Part 1 is the length of your hypothesis. Just think of this as the cost of writing down your theory. A simple rule like add 2 is super short to explain. A crazy complex polynomial would take pages and pages. Then you have part 2, the length of the data after you've applied your theory. This is all about how well your theory actually fits the data.
The real goal, then, is to minimize the sum of these 2 things together. You can't just focus on one. Sure, you could have a really simple theory, but if it doesn't fit the data, that second part is going to be huge. Or you could have a theory that fits the data perfectly, but if the theory itself is incredibly complex, the first part will be off the charts. The best model is the one that finds that perfect sweet spot.
And it turns out this balancing act is exactly what we need to solve one of the biggest headaches in artificial intelligence and statistics, a problem called overfitting.
Overfitting is what happens when a model is, well, it's almost too flexible. It has so many knobs and dials it can twist that it can bend and curve to hit every single data point you give it. And on the surface, it looks amazing, a perfect fit. But here's the kicker, it's an illusion. The model hasn't actually learned the deep underlying pattern. It has just memorized the specific data it was trained on, including all the random flukes and errors, all that noise. It's like a student who memorizes the exact answers to a practice test, but has zero clue how to solve any new problems.
So how do we stop our models from becoming these perfect little memorizers? How does this minimum description length principle save the day?
Well, it all comes back to that 2-part code we talked about. That first part, the length of the hypothesis, acts like a penalty flag. It directly punishes a model for being too complex. An overfitted model is, by its very nature, incredibly complex, so its description length blows up. MDL will naturally prefer the simpler model that actually captures the real signal. And this whole idea isn't just a clever trick. It's built on a deep mathematical foundation called Kolmogorov complexity.
And it's the basis for even more advanced methods that get really smart about this stuff.
Okay, so why should you really care about any of this? Because this isn't just some technical tool for data scientists. The compression principle is way bigger than that. It's offering us a kind of universal theory for how any system, whether it's a human brain or a computer, can genuinely learn from the world around it.
And its reach is just massive. In cognitive science, it helps explain how we make sense of everything. In AI, it's a cornerstone for building machines that don't just memorize. And in the philosophy of science, it gives us a real mathematical backbone for an idea you've probably heard of, Occam's razor, the idea that the simplest explanation is usually the best one.
It all comes back to compression. As the source material puts it so well, you can judge any model by its ability to compress a data set. In other words, how good is it at finding that useful information and separating it from all the random junk?
So, if there's one thing you walk away with today, let it be this. True learning, real intelligence, isn't about how much stuff you can cram into your head. It's about how well you can explain things. It's this constant search for the simplest, most powerful explanation, the best compression that unlocks the real structure of the world.
And that leads us to one last big question to chew on. If this powerful idea is true, if learning really is, at its core, just a kind of data compression, what does that imply? What about things like creativity, or consciousness, or understanding? What might this beautiful, elegant theory still be leaving out?